Hello, my friend. Welcome back to the Sleepy Professor channel. I'm glad to see you again. Tonight we're going on a gentle journey through our solar system and beyond. A peaceful voyage where we'll discover the quiet wonders of distant worlds, the soft glow of planets spinning in the darkness, and the calming rhythms of celestial bodies that have been dancing through space for billions of years. So settle in, get comfortable, and let your mind drift among the planets as we explore together. Let's begin with something truly mesmerizing. Did you know that Saturn's rings are made almost entirely of water ice? Imagine countless billions of ice particles, each one catching and reflecting sunlight, creating that beautiful, shimmering band we see from Earth. Some of these ice chunks are as small as grains of sand, while others are as large as mountains, all slowly orbiting in perfect harmony. And speaking of Saturn's rings, they're surprisingly thin. If you could stand them upright, they'd stretch from Earth to the Moon, yet they're only about 30 feet thick in most places. It's like an enormous cosmic sheet of paper, delicate and elegant, floating in the vastness of space. Now, let me tell you about something wonderfully peaceful on Venus. A single day on Venus lasts longer than its entire year. The planet rotates so slowly on its axis that by the time it completes one full rotation, it has already travelled around the Sun. Imagine waking up and knowing that your day will last 243 Earth days, while your year is only 225 Earth days. Time moves differently there, in its own gentle, unhurried way. And here's something even more intriguing about Venus. It rotates backwards compared to most other planets. If you could stand on Venus and watch the Sun, it would rise in the west and set in the east. Scientists call this retrograde rotation, and it gives Venus its own unique rhythm in our solar system's grand dance. Let's drift over to Mercury now, the closest planet to our Sun. Mercury has the most eccentric orbit of all the planets, meaning its path around the Sun is more oval-shaped than circular. Sometimes it's much closer to the Sun, and sometimes it's farther away, creating dramatic temperature differences across its surface. It's a world of extremes, yet there's something fascinating about its solitary journey so close to our star. On Mercury, you'd experience something quite peculiar with the Sun's movement. Because of the planet's unusual orbit and rotation, there are spots on Mercury where the Sun appears to rise, then set, then rise again, all in the same Mercurian day. It's like the universe is gently rocking the Sun back and forth in the sky. Now, let me take you to Jupiter, the giant of our solar system. Jupiter's Great Red Spot is actually a storm that's been raging for at least 400 years. That's right, a storm older than most countries on Earth, swirling peacefully in Jupiter's atmosphere. It's large enough that 3 Earths could fit inside it, and it continues its slow, majestic rotation, a testament to the enduring nature of planetary weather systems. And while we're at Jupiter, consider this. The planet doesn't have a solid surface. If you could somehow descend into Jupiter, you'd pass through layers of gas that gradually become denser and denser, eventually transitioning into liquid, but you'd never find ground to stand on. It's an ocean of gas and liquid, swirling and mixing in an endless fluid dance. Jupiter also has at least 95 known moons, each one a world unto itself. Among them is Ganymede, the largest moon in our entire solar system. Ganymede is even bigger than the planet Mercury, and it's the only moon known to have its own magnetic field. Imagine a moon so substantial it behaves almost like a planet itself. Let's visit Europa, another one of Jupiter's moons. Beneath its icy surface lies an ocean that contains more water than all of Earth's oceans combined. This hidden sea, warmed by tidal forces from Jupiter's immense gravity, might be one of the best places in our solar system to search for life. It's peaceful to think about, an entire ocean world locked beneath ice, quiet and dark and full of possibility. Moving outward to Mars, the red planet, we find something surprisingly gentle. Snow. Mars has snowfall, though it's not quite like the snow we know. Martian snow is made of carbon dioxide or dry ice, and it falls softly from the planet's clouds during the winter. There's also water ice snow in some regions, drifting down through the thin Martian air. Mars also has the tallest volcano in the entire solar system. Olympus Mons rises about 16 miles high, nearly 3 times the height of Mount Everest. But here's the peaceful part. Olympus Mons is what we call a shield volcano, which means it has gentle, sloping sides. If you were to climb it, you'd barely notice the incline in many places. It's a mountain so vast that if you stood on its summit, the base would be beyond the horizon. And on Mars, sunsets are blue. While Earth's sunsets paint the sky in reds and oranges, Martian sunsets glow with a cool, tranquil blue around the sun. This happens because of the fine dust particles in Mars' atmosphere, which scatter light differently than Earth's air does. It's a serene, otherworldly sight. Let me tell you about something fascinating. Mars has seasons, just like Earth. This happens because Mars, like Earth, has a tilted axis. As Mars orbits the Sun, different parts of the planet receive more or less sunlight, creating spring, summer, fall, and winter. However, Martian seasons last about twice as long as Earth's, because Mars takes longer to orbit the Sun. Now, let's drift back to our own planet for a moment to appreciate something special. Earth is the only planet in our solar system not named after a god or goddess from Greek or Roman mythology. Instead, our planet's name comes from old Germanic and English words meaning ground or soil. There's something humble and grounding about that, don't you think? And speaking of Earth, our planet has a gentle hum. Scientists have discovered that Earth produces a constant low-frequency hum that's too quiet for human ears to detect. It's like our planet is singing a soft lullaby to the universe, a peaceful vibration from the movement of ocean waves and atmospheric pressure changes. Let's journey to Neptune now, the beautiful blue giant at the edge of our solar system. Neptune has the strongest winds in the solar system, with wind speeds reaching up to some 200 miles per hour. Yet despite these fierce winds, there's something calming about Neptune's consistent deep blue colour, created by methane in its atmosphere absorbing red light. Neptune takes 165 Earth years to complete one orbit around the Sun. Think about that for a moment. Since Neptune was discovered in 1846, it only completed its first full orbit around the Sun in 2011. It's a world that moves through time at its own patient, unhurried pace, and Neptune has 14 known moons, with Triton being the largest. Triton is unique because it orbits Neptune backwards, opposite to the planet's rotation. Scientists believe Triton was once a separate object from the Kuiper belt that Neptune captured long ago. It's like Neptune reached out and gently pulled this wandering world into its embrace. Let's talk about Uranus now, the tilted ice giant. Uranus rotates on its side, with its axis tilted at about 98 degrees. This means that for part of its orbit, one pole points almost directly at the Sun, giving that pole continuous daylight for 42 Earth years, followed by 42 years of darkness. It's an extreme cycle, yet it continues steadily, year after year. Uranus appears as a pale blue-green colour, and it's remarkably calm in appearance. Unlike Jupiter and Neptune with their visible storms and bands, Uranus presents an almost featureless face to space, like a smooth, tranquil sphere floating in the darkness. Here's something intriguing. Uranus has 27 known moons, and they're all named after characters from the works of William Shakespeare and Alexander Pope. Names like Titania, Oberon, Miranda, and Ariel. It's lovely to think of these distant moons carrying the names of literary characters through the cosmos. Now, let me share something about planetary orbits that's quite soothing. All the planets orbit the Sun in the same direction, like a cosmic carousel slowly turning. This happened because our solar system formed from a spinning disk of gas and dust, and that original spin is still preserved in the planet's orbits billions of years later. Let's return to Saturn for a moment. Saturn is the least dense planet in our solar system. In fact, if you could find a bathtub large enough, Saturn would float in it. Imagine this enormous planet, nearly 10 times the diameter of the Earth, gently floating like a beach ball. It's about 95% the density of water, made mostly of hydrogen and helium. Saturn also has a hexagonal storm at its north pole. This six-sided jet stream is larger than Earth and has been swirling there for decades. Each side of the hexagon is longer than the diameter of our planet. It's a perfect geometric shape created naturally by atmospheric winds, a mesmerizing pattern spinning in the clouds. And here's something gentle about Saturn. It has over 80 moons, creating a complex system of gravitational interactions. Some of these moons actually help shape Saturn's rings, acting as shepherd moons that keep particles confined to certain areas. It's like they're carefully tending to the rings, maintaining their structure through their gravitational influence. Let me tell you about a moon of Saturn called Enceladus. This small, icy moon shoots geysers of water ice into space from cracks in its surface. These plumes can reach hundreds of miles high, creating a faint ring around Saturn. Beneath Enceladus's icy shell is another hidden ocean, warmed by tidal heating, quietly, existing in the cold reaches of the outer solar system. Moving to something broader, planets are kept in their orbits by a perfect balance. The Sun's gravity pulls them inward, while their sideways motion keeps them from falling in. It's like they're constantly falling toward the Sun, but moving fast enough sideways that they keep missing it. This delicate balance has been maintained for over 4.5 billion years. Let's think about planetary rings for a moment. They're not unique to Saturn. Jupiter, Uranus, and Neptune all have ring systems too, though they're much fainter and harder to see. Each planet's rings tell a story of moons that got too close, or asteroids that wandered into harm's way, breaking apart to create these beautiful thin bands of debris. Here's something peaceful to consider. The Earth's moon is slowly drifting away from us, moving about 1.5 inches farther from Earth each year. This has been happening for billions of years, and it will continue. The tidal forces between Earth and the Moon cause this gradual separation, a slow cosmic waltz where the partners are incrementally moving apart. And speaking of our Moon, it always shows us the same face. The Moon is tidally locked to Earth, meaning its rotation period matches its orbital period. This happened over millions of years due to Earth's gravitational influence, eventually synchronizing the Moon's rotation. The far side of the Moon, which we never see from Earth, remained a mystery until spacecraft photographed it. Let's journey to the asteroid belt between Mars and Jupiter. This region contains countless rocky objects, but despite what science fiction might suggest, it's mostly empty space. If you were in a spacecraft flying through the asteroid belt, you likely wouldn't see a single asteroid out your window. They're spread across such a vast area that encounters are rare. The largest object in the asteroid belt is Ceres, which is actually classified as a dwarf planet. Ceres is round like a planet, and it contains about a third of the asteroid belt's total mass. It even has a water ice beneath its surface, and possible signs of a subsurface ocean. It's a peaceful little world, quietly orbiting between the rocky and gas giant planets. Let me share something about planetary formation that's quite remarkable. Planets form from dust. In the early solar system, tiny particles of dust and ice stuck together through static electricity and gentle collisions. Over millions of years, these clumps grew larger and larger, their gravity increasing, allowing them to pull in more material, eventually becoming the planets we see today. Here's a calming thought. Every planet in our solar system fits comfortably within the space between Earth and our Moon. If you placed all the planets side by side, their combined diameter would be about 230,000 miles, while the average distance from Earth to the Moon is about 238,000 miles. There'd even be some room to spare. Now let's talk about something called libration. Although the Moon shows us the same face, it actually rocks slightly back and forth and up and down over time. This gentle motion means that from Earth, we can actually see about 59% of the Moon's surface over time, not just 50%. It's like the Moon is slowly nodding and shaking its head over the course of its orbit. Venus has more volcanoes than any other planet in our solar system, with over 1,600 major volcanoes dotting its surface. Most of these are dormant, quietly standing on a surface hot enough to melt lead, beneath an atmosphere thick with clouds of sulfuric acid. Yet there's a strange beauty in imagining this volcanic landscape, ancient and still. The atmosphere of Venus is so dense that it creates enormous pressure at the surface, about 92 times greater than Earth's pressure at sea level. It's like being 3,000 feet underwater in Earth's oceans. This pressure is so intense that if you could stand on Venus, the carbon dioxide atmosphere would feel almost like a thick fluid around you. Let's visit Mercury's terminator line, the boundary between its day and night sides. Because Mercury rotates so slowly, this line moves very slowly across the surface. There are permanently shadowed craters near Mercury's poles, where sunlight has never reached. And in these cold, dark places, scientists have found evidence of water ice, preserved for perhaps billions of years. Here's something gentle about planetary temperatures. On the night side of Mercury, temperatures drop to about minus 290 degrees Fahrenheit, while the day side soars to 800 degrees Fahrenheit. Yet in those permanently shadowed craters, the temperature remains constant and frigid, creating these pockets of ice on one of the hottest planets in the solar system. Jupiter's moon Io is the most volcanically active body in the solar system. It has hundreds of active volcanoes, constantly erupting, reshaping the moon's surface. This happens because of the gravitational tug-of-war between Jupiter and its other large moons, which squeezes and flexes Io's interior, keeping it molten. Despite the violence of these eruptions, there's a rhythm to it, a constant geological heartbeat. Another of Jupiter's moons, Callisto, is one of the most heavily cratered objects in the solar system. Its ancient surface is covered with impact craters, a record of billions of years of collisions. Looking at Callisto is like reading a history book written in stone, each crater a marker of a moment when something from space touched this distant moon. Let me tell you about planetary migration. When our solar system was young, planets didn't stay in the same places they formed. They drifted inward and outward, pushed and pulled by gravitational interactions with each other and with the disk of material surrounding the young sun. Jupiter may have wandered closer to the sun and then back out again, its journey reshaping the entire architecture of our solar system. Mars's two small moons, Phobos and Deimos, are probably captured asteroids. They're irregularly shaped and tiny compared to Earth's moon. Phobos orbits so close to Mars and so quickly that it rises in the west and sets in the east, moving across the sky in the opposite direction to Mars's rotation. It completes an orbit in just over 7 hours. And here's something bittersweet about Phobos. It's slowly spiraling inward toward Mars. In about 50 million years, it will either crash into Mars or break apart to form a ring around the planet. Until then, it quietly orbits, drawing imperceptibly closer with each pass. Let's think about the calm of planetary years. On Venus, you'd celebrate your birthday every 225 Earth days. On Mercury, every 88 Earth days. But on Neptune, you'd wait 165 Earth years for a single birthday. Time is relative, measured differently on each world, each planet keeping its own peaceful pace through the cosmos. Earth's axis wobbles very slowly over time, completing one wobble every 26,000 years or so. This is called precession, and it means that the North Star hasn't always been our North Star, and it won't always be. Currently, Polaris marks north, but thousands of years ago it was Thuban, and thousands of years in the future it will be Vega. The stars themselves seem to slowly drift in a great circle overhead. Here's something tranquil. The planets move in ellipses, not perfect circles. These oval orbits were discovered by Johannes Kepler, who found that planets move faster when they're closer to the Sun and slower when they're farther away. It's a natural rhythm, speeding up and slowing down, like breathing as they journey around our star. The gas giants, Jupiter, Saturn, Uranus, and Neptune, all have something in common. They're much larger than the rocky inner planets, yet they're made of lighter materials. They're enormous balloons of gas, mostly hydrogen and helium, with relatively small rocky cores buried deep beneath thousands of miles of atmosphere. Let me share something about Jupiter's magnetosphere, the magnetic field surrounding the planet. It's the largest structure in our solar system, extending millions of miles into space. If you could see it with your eyes, it would appear larger than the full moon in our night sky, even though Jupiter is so far away. This invisible shield protects Jupiter and its moons from the solar wind. Saturn's moon Titan is larger than the planet Mercury and has a thick atmosphere, the only moon in our solar system with a substantial atmosphere. This atmosphere is mostly nitrogen, like Earth's, but it's much thicker. Titan's atmospheric pressure at the surface is about 1.5 times Earth's, and it's perpetually shrouded in a hazy orange smog. And on Titan, there are lakes and seas, but they're not filled with water. Instead, they contain liquid methane and ethane, hydrocarbons that are gas on Earth but liquid in Titan's cold environment, which hovers around -290 degrees Fahrenheit. Rain falls on Titan, not water rain but methane rain, filling rivers that flow to these hydrocarbon seas. Let's drift to something called orbital resonance. Some moons orbit in synchronization with each other. For example, 3 of Jupiter's large moons, Io, Europa and Ganymede, are locked in a pattern where for every 4 orbits Io makes, Europa makes 2 and Ganymede makes 1. They're connected in a gravitational rhythm, their orbits forever linked in this mathematical harmony. Here's a peaceful fact about planetary colours. Each planet has its own distinct hue. Mercury is grey, Venus is yellowish-white, Earth is blue and white, Mars is red, Jupiter is orange and white, Saturn is golden, Uranus is pale blue-green, and Neptune is deep blue. Together, they create a palette of colours spanning the solar system, each one unique and beautiful. The Earth's atmosphere scatters blue light more than other colours, which is why our sky appears blue during the day. But this same effect works differently on other planets. Mars's sky is butterscotch during the day and blue at sunset. It's the opposite of Earth, a reminder that familiar rules change when you travel to other worlds. Let me tell you about something called the Roche limit. This is the distance within which a moon or other object held together only by its own gravity will be torn apart by a planet's tidal forces. Saturn's rings exist within Saturn's Roche limit, which is why they can't coalesce into a moon. Any moon that ventures too close would be gently pulled apart by tidal forces. Venus has enormous mountains and vast plains. One of its mountain ranges, Maxwell Montes, rises about 7 miles high. But with no water to erode it and only gentle volcanic activity, the landscape changes very slowly. These mountains have stood for hundreds of millions of years, slowly weathering in the dense, hot atmosphere. Here's something soothing about planetary protection. Earth's magnetic field shields us from harmful solar radiation and particles from space. This magnetic field is generated by the movement of molten iron in Earth's outer core, creating an invisible protective bubble around our planet. It's been quietly protecting life on Earth for billions of years. Other planets have magnetic fields too. Jupiter's is particularly strong, about 20,000 times more powerful than Earth's. Mercury has a weak magnetic field, while Venus and Mars have essentially none. Each planet's magnetic field, or lack thereof, tells us something about what's happening deep inside the planet. Let's think about the music of the spheres. Ancient astronomers believed that the planets produced harmonious music as they moved through space, a cosmic symphony too subtle for human ears. While we now know planets don't literally create sound in the vacuum of space, there's still something poetic about the idea of planets moving in mathematical harmony, each in its own orbit, creating patterns and rhythms. NASA has actually recorded electromagnetic vibrations from planets and converted them into sound, creating eerie, beautiful audio representations. Jupiter sings with whistles and whooshes, Saturn creates ghostly howls, and Earth produces a kind of rushing wind sound mixed with chirps. In a way, the ancient astronomers weren't entirely wrong. The planets do have their own voices. Here's something about planetary spin. Most planets rotate in the same direction they orbit the Sun, counterclockwise as viewed from above the Sun's north pole. Venus and Uranus are the exceptions, with Venus rotating clockwise and Uranus rolling along on its side. It's as if most planets agreed on a direction, but a few decided to be different. The length of a day varies dramatically from planet to planet. Jupiter, despite being the largest planet, has the shortest day, rotating once every 10 hours. Saturn's day is about 10.5 hours. On the other end, Venus takes 243 Earth days to rotate once. Each planet has its own relationship with time. Let me share something about Mars's polar ice caps. They're made of both water ice and frozen carbon dioxide. In the Martian winter, carbon dioxide from the atmosphere freezes out, adding a layer of dry ice to the polar caps. In spring and summer, this dry ice sublimes directly back into gas, and the caps shrink. It's a yearly cycle, the planet breathing in and out. There are enormous volcanoes on Mars that have been extinct for millions of years. The lava flows from these ancient eruptions are still visible, frozen in time. Some of these flows extend for hundreds of miles, showing the path that molten rock once took across the Martian surface before cooling and solidifying billions of years ago. Here's a thought about planetary exploration. Every planet and moon we've visited with spacecraft has surprised us. We expected certain things and found others. Mars had dry riverbeds, Europa had a hidden ocean, Enceladus had geysers, Titan had lakes. Each new discovery reminds us that the universe is full of wonders we haven't yet imagined. The Great Red Spot on Jupiter is slowly shrinking. Historical observations show it was much larger in the past. Scientists aren't entirely sure why it's getting smaller, but they continue to study this ancient storm, watching its gradual transformation over decades and centuries. Saturn's rings cast shadows on the planet below, creating dark bands across Saturn's clouds. When Saturn's orbit brings it to certain angles relative to the Sun, these shadows become particularly pronounced, like the shadow of a cosmic sundial marking the passage of time across Saturn's face. Let's consider the planet's densities. The rocky planets, Mercury, Venus, Earth and Mars, are dense and compact, made of rock and metal. The gas giants are much less dense, made mostly of light elements. Saturn is so light it would float in water if you could find an ocean large enough. Neptune, despite being an ice giant, is still denser than Saturn but much less dense than Earth. Here's something about the spacing of planets. There's a rough pattern called the Titius-Bode law that approximately describes the distances of planets from the Sun. It's not a perfect rule and doesn't work for Neptune, but it shows there's a kind of order to planetary spacing, each world occupying its own zone in a loosely organized solar system. The asteroid belt isn't evenly distributed. There are gaps called Kirkwood gaps where you'll find very few asteroids. These gaps occur at distances from the Sun where an asteroid's orbital period would be a simple fraction of Jupiter's orbital period. Jupiter's gravity has swept these regions clean over millions of years, creating these quiet, empty zones. Let me tell you about something called tidal locking. When a moon or planet is tidally locked to another body, it always shows the same face to that body. Our moon is tidally locked to Earth. Mercury is in a special resonance with the Sun, rotating 3 times for every 2 orbits. Many moons in our solar system are tidally locked to their planets, frozen in an eternal gaze. Venus is sometimes called Earth's twin because of their similar sizes, but their surfaces couldn't be more different. While Earth has oceans and continents, forests and ice caps, Venus has a scorching surface of volcanic plains and rocky plateaus, all hidden beneath thick clouds. It's a reminder that planets can start similar but evolve in drastically different directions. Here's something calming. The planets have been orbiting the Sun for over 4.5 billion years, through countless days and nights, seasons and years, in a cosmic routine that predates life on Earth, predates the dinosaurs, predates the formation of Earth's moon. They'll continue their patient orbits for billions of years to come. Earth experiences about 12 lunar months in a year, because that's roughly how long it takes the moon to orbit Earth 12 times, while Earth orbits the Sun once. Other planets with moons have different calendar systems. Jupiter's moons orbit at various speeds, some completing an orbit in just 42 hours, others taking over 2 Earth years. The planets all orbit roughly in the same plane, like marbles rolling around on a slightly tilted tabletop. This flat disk-like arrangement is left over from the original disk of gas and dust, from which the solar system formed. It's why, when you look at pictures of the solar system, all the planets seem to line up in a row. Let's think about planetary names and their origins. Mercury, the swift messenger god, for the fastest orbiting planet. Venus, the goddess of beauty, for the brightest planet in our sky, Mars, the god of war, for the red planet, Jupiter, king of the gods, for the largest planet, Saturn, god of time and agriculture, Uranus, the ancient Greek god of the sky, Neptune, god of the sea, for the blue planet at the edge of the system. Here's something gentle about comets visiting from far away. Many comets come from the Oort cloud, a spherical shell of icy bodies surrounding our solar system far beyond Pluto. When one is nudged inward, it begins a journey toward the sun that might take thousands of years, silently gliding through the darkness until it finally enters the inner solar system and begins to glow. The planets protect Earth in small ways. Jupiter, with its immense gravity, has caught or deflected countless asteroids and comets that might otherwise have struck the inner planets. It acts as a kind of cosmic guardian, though not perfectly. Some impactors still make it through, but Jupiter's presence has likely prevented many potential catastrophes. Mars has seasons because, like Earth, its rotational axis is tilted. This tilt is currently about 25 degrees, quite similar to Earth's 23.5 degrees, but Mars's tilt changes more dramatically over time, sometimes increasing to 60 degrees, which would create extremely severe seasonal variations. Right now it's in a relatively stable period. Let me share something about exoplanets, planets orbiting other stars. We've discovered thousands of them, and they've shown us that planetary systems come in endless varieties. Some planets orbit incredibly close to their stars, completing an orbit in days. Others are lonely wanderers, ejected from their systems to drift through the galaxy. Some are hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. There are super-Earths, planets larger than Earth but smaller than Neptune. There are ice giants and lava worlds, planets with diamond rain and planets with iron snow. The diversity is stunning, and it reminds us that our solar system is just one possible arrangement among countless others. Here's a peaceful thought. Light from the sun takes about 8 minutes to reach Earth. When you feel sunshine on your face, you're feeling light that left the sun 8 minutes ago. Light takes about 43 minutes to reach Jupiter and about 4 hours to reach Neptune. The solar system is so vast that even light, the fastest thing in the universe, takes hours to cross it. The Earth's atmosphere is precious and thin. If the Earth were the size of an apple, the atmosphere would be thinner than the apple's skin. This delicate shell of air is all that separates us from the vacuum of space, and it's held in place by Earth's gravity, a gentle but constant force. Let's consider the beauty of eclipses. On Earth, we experience solar eclipses because the moon is exactly the right size and distance to perfectly cover the sun's disk. This is a cosmic coincidence. The sun is about 400 times larger than the moon, but it's also about 400 times farther away, so they appear the same size in our sky. Other planets have eclipses too. Mars's moons are too small to completely cover the sun, so they create partial eclipses. Jupiter's moons cast shadows on Jupiter's clouds, creating dramatic dark spots that drift across the planet's face. Saturn's moons eclipse the sun as seen from Saturn, though the view would be obscured by Saturn's rings. Here's something about the colour of atmospheres. Atmospheric particles scatter light, and different size particles scatter different wavelengths. This is why Earth's sky is blue, why sunsets are red, and why Mars's sky is butterscotch. Each planet's atmosphere creates its own signature colours based on its composition and the size of particles suspended in it. The temperature of a planet depends on many factors: distance from the Sun, atmospheric thickness, and even the colour of its surface. Darker surfaces absorb more heat, while lighter surfaces reflect it. Venus, despite being farther from the Sun than Mercury, is hotter because its thick atmosphere traps heat in a runaway greenhouse effect. Let me tell you about planetary wobble. When we detect exoplanets around other stars, we often find them by watching the star wobble slightly. The planet's gravity tugs on the star as it orbits, causing the star to move in a tiny circle or ellipse. By measuring this wobble, we can determine the planet's mass and orbit without ever seeing the planet directly. Saturn's rings are divided into sections separated by gaps. The largest gap, the Cassini division, was discovered in 1675 and is wide enough that you could fit the planet Mercury inside it. This gap exists because of a resonance with Saturn's moon Mimas, whose gravity clears out ring particles at that distance. Here's a soothing fact. The planets have been companions to each other for their entire existence. They formed together from the same cloud of gas and dust, and they've shared the same solar system for billions of years. In a sense, they're siblings, born from the same material, shaped by the same forces, forever bound together by the Sun's gravity. The atmospheres of the gas giants are dynamic, with winds, storms, and clouds constantly shifting and changing. Yet beneath this activity there's a consistency, a pattern. Jupiter's bands of clouds, Saturn's hexagonal storm, Neptune's dark spots, these features persist for years or decades, showing that even chaos has its rhythms. Let's think about the view from different planets. From Mercury, the Sun would appear more than twice as large as it does from Earth. From Neptune, the Sun would look like a bright star, providing only 9/100th the light we receive on Earth. Yet it would still be by far the brightest object in Neptune's sky, a distant beacon marking home. Earth is the only planet known to have plate tectonics, where the surface is divided into moving plates that slowly drift, collide, and subduct over millions of years. This geological activity recycles material between the surface and interior, creating mountains, ocean trenches, and volcanic activity. It's a slow, constant reshaping of our world. Here's something about the formation of planets. They grow from tiny dust grains that stick together through static electricity, gradually building larger clumps. These clumps collide and merge, growing into planetesimals, then protoplanets, and finally planets. The process takes millions of years, but it's driven by simple forces: gravity, friction, and countless gentle collisions. Mars once had a thicker atmosphere and possibly liquid water on its surface. Ancient riverbeds and lake beds carved into its surface suggest a wetter past. Over time, Mars lost most of its atmosphere, probably because it lacks a strong magnetic field to protect against solar wind. The atmosphere slowly leaked into space, and the planet dried out, leaving the cold, arid world we see today. Let me share something about synchronous rotation. Many moons rotate at the same rate they orbit their planet, so they always show the same face. This happens because the planet's gravity creates a tidal bulge on the moon, and over millions of years this bulge acts like a brake, slowing the moon's rotation until it matches its orbital period. The planets emit heat as well as reflect sunlight. Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, powered by heat left over from their formation and by gravitational compression in their interiors. They're slowly cooling down, a process that will continue for billions of years. Here's something calming about orbital periods. They're predictable and constant. we can calculate exactly where each planet will be hundreds or thousands of years in the future or past. This predictability allowed ancient astronomers to chart the heavens and create calendars. It's a clockwork universe, each planet a gear in a cosmic mechanism that runs with perfect precision. The rocky planets have cores made of iron and nickel. We know this from studying their densities and from measuring their magnetic fields. Earth's core is partially molten, creating our magnetic field as it circulates. Mercury has a large iron core that makes up a substantial fraction of its volume, which is why Mercury is so dense despite being small. Saturn's moon Mimas has a giant crater called Herschel that makes it look like the Death Star from Star Wars. The impact that created this crater nearly destroyed Mimas. The shock waves from the impact travelled through the moon and converged on the opposite side, creating disrupted terrain there. Mimas survived, but barely, and it carries this scar as evidence of a catastrophic collision billions of years ago. Let's consider the silence of space. There's no sound in the vacuum between planets, because sound needs a medium like air or water to travel through. The planets move in perfect silence, never disturbing the quiet. Only when spacecraft enter a planet's atmosphere do they begin to hear the rush of wind and the crackle of atmospheric phenomena. Here's something wonderful about Jupiter's moon Callisto. It's thought to have a subsurface ocean, like Europa and Enceladus. This ocean would be sandwiched between layers of ice deep beneath the ancient cratered surface. It's peaceful to imagine these hidden oceans, quiet and dark, existing for billions of years beneath ice shells, untouched and unexplored. The planets have different numbers of moons, and this tells us about their history. Jupiter and Saturn, being massive and far from the Sun, were able to capture many moons from the surrounding material when the solar system was forming. Mars, being smaller and closer to the Sun where there was less material, captured only 2 tiny moons. Each planetary system is shaped by its location and size. Let me tell you about something called orbital eccentricity. A perfectly circular orbit has an eccentricity of 0, while more elliptical orbits have higher eccentricities. Mercury has the most eccentric orbit of any planet, at 0.21. Venus has the least eccentric, at 0.007, making its orbit nearly a perfect circle. These numbers describe the shape of each planet's path through space. Here's a gentle fact about Neptune's moon Triton. It has geysers that spray nitrogen gas and dark material several miles into its thin atmosphere. These geysers are thought to be driven by sunlight warming nitrogen ice beneath Triton's surface, causing it to sublimate and burst through weak points in the crust. Even in the cold outer solar system, worlds remain geologically active. The planets don't all orbit at the same speed. Mercury races around the Sun at about 105,000 miles per hour. Earth travels at about 67,000 miles per hour. Neptune, so far from the Sun, moves at only about 12,000 miles per hour. Yet each planet is moving at exactly the right speed for its distance, maintaining a perfect balance between gravity and motion. Let's think about the age of planets. All the planets in our solar system formed at roughly the same time, about 4.6 billion years ago. They're ancient beyond human comprehension, yet they're middle-aged compared to the universe itself, which is about 13.8 billion years old. They've existed for a third of the universe's entire history. Here's something about planetary atmospheres and escape velocity. Lighter gases like hydrogen and helium move faster at a given temperature than heavier gases. If a planet's gravity isn't strong enough, these light gases can reach escape velocity and drift away into space. That's why small planets like Mars and Mercury have thin atmospheres. They couldn't hold on to their lighter gases over billions of years. The gas giants helped shape the inner solar system. In the early days of our solar system, Jupiter and Saturn's gravity influenced the orbits of smaller bodies, flinging some into the Sun, others out of the solar system entirely, and some inward toward the rocky planets. This gravitational gardening helped determine which asteroids and comets ended up where. Let me share something about Mars's atmosphere. It's about 100 times thinner than Earth's, composed mostly of carbon dioxide. Standing on Mars, you wouldn't be able to breathe, and the low pressure would be dangerous. Yet this thin atmosphere is enough to create weather, dust storms that can engulf the entire planet, and those beautiful blue sunsets we mentioned earlier. Here's a calming thought about planetary orbits. They're stable over timescales we can barely imagine. Computer simulations suggest that the current configuration of planets could remain stable for billions of years into the future. The planets have found a harmonious arrangement, and they'll likely maintain it until the Sun itself begins to die, some 5 billion years from now. Venus's clouds are made of sulfuric acid droplets, created when sulfur dioxide from volcanic eruptions combines with water vapor high in the atmosphere. These clouds completely obscure the surface, making Venus the brightest natural object in our night sky after the Moon. The clouds reflect about 75% of the sunlight that hits them, giving Venus its brilliant appearance. The concept of a year varies dramatically across planets. We've mentioned this before, but it's worth considering more deeply. A year is simply one complete orbit around the Sun. For Mercury, a year passes in just 88 Earth days. For Neptune, a year is 165 Earth years. Imagine living on Neptune and experiencing each season for over 40 Earth years at a time. Let's visit Uranus's moon Miranda, one of the most geologically diverse bodies in the solar system. Its surface shows enormous canyons, terraced layers, and a mix of old cratered terrain alongside newer grooved areas. Scientists think Miranda might have been shattered by an impact and then reassembled, with the pieces coming back together in a jumbled arrangement. It's a world with a violent past now frozen in time. Here's something about the Sun's influence. The solar wind, a stream of charged particles flowing from the Sun, reaches all the planets. Earth's magnetic field deflects most of these particles, creating the auroras near our poles. Jupiter's powerful magnetic field creates even more spectacular auroras, while planets without magnetic fields like Venus and Mars face the solar wind more directly, gradually losing atmospheric particles to space. The inner planets, Mercury, Venus, Earth, and Mars, are sometimes called terrestrial planets because they're rocky and Earth-like in composition. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are called Jovian planets after Jupiter, or gas and ice giants. This division reflects the two basic types of planets that formed in different regions of the early solar system. Let me tell you about something called the frost line or snow line in the early solar system. This was the distance from the Sun where it was cold enough for volatile compounds like water, ammonia, and methane to condense into solid ice grains. Beyond this line, in the outer solar system, there was much more material available for planets to form from, which is why the gas giants grew so large. Here's a peaceful fact. The planets reflect sunlight. They don't produce their own visible light. When you see Venus shining in the evening sky, you're seeing sunlight bouncing off its clouds. When you see Jupiter, you're seeing sunlight reflected from its cloud tops. They're all illuminated by the same sun that lights our days, just from different distances and angles. Saturn's rings are incredibly thin compared to their width. If you made a scale model where the rings were as thin as a piece of paper, they would be about a mile wide. Despite this thinness, they contain countless trillions of individual particles, each on its own orbit around Saturn, collectively creating those magnificent rings we see through telescopes. The planets have been objects of wonder throughout human history. Ancient peoples watched them move against the background stars and called them wanderers. They wove myths around them, used them to track seasons and create calendars, and pondered their nature. For most of human history, we could only observe planets as distant lights in the sky. Now we've sent spacecraft to all of them, transforming them from mysterious lights into real, physical worlds. Let's consider the phases of planets. Just like the Moon, planets can show phases when viewed from the right location. From Earth, we can see Venus go through a full set of phases, from crescent to full and back. Mercury also shows phases. Mars can appear slightly gibbous when it's farther from us than the Sun. Each phase is a reminder that these are three-dimensional worlds illuminated by the Sun. Here's something about Uranus's discovery. It was the first planet discovered with a telescope, found by William Herschel in 1781. Before that, only the 5 planets visible to the naked eye were known: Mercury, Venus, Mars, Jupiter, and Saturn. Uranus's discovery doubled the known size of the solar system overnight, and showed that there might be more worlds waiting to be found. And indeed, Neptune was. Discovered in 1846, found not by accident but through mathematics. Astronomers noticed that Uranus's orbit wasn't quite right, as if something was tugging on it. They calculated where an unknown planet would need to be to cause this effect, pointed their telescopes at that spot, and there was Neptune, right where the math predicted. It was a triumph of human understanding over cosmic mystery. Let me share something about tidal forces. They're caused by the difference in gravitational pull on the near and far sides of an object. The Moon's gravity pulls harder on the side of Earth facing it than on the far side, creating a tidal bulge. These same forces heat the interiors of some moons, like Io and Europa, keeping them geologically active despite being so far from the Sun. Here's a calming thought about the Kuiper Belt, a region beyond Neptune filled with icy bodies. Pluto resides here, along with other dwarf planets like Eris, Makemake, and Haumea. These are distant frozen worlds, moving slowly through the darkness at the edge of our solar system. They're so far away that the Sun provides barely any warmth, and they exist in a perpetual twilight. The planets all formed from the same cloud of gas and dust, which means they're all made of the same basic elements, just in different proportions. The inner planets lost most of their lighter elements and kept the heavier rocks and metals. The outer planets retained huge amounts of hydrogen and helium, but fundamentally, all the planets, all the moons, and even you and I are made of the same star stuff, recycled from earlier generations of stars. Let's think about crater formation. When an asteroid or comet hits a planet or moon, it creates a crater. The size of the crater depends on the size and speed of the impactor. These craters are like clocks in a way. Older surfaces have more craters because they've had more time to accumulate impacts. Younger surfaces, recently resurfaced by volcanic activity or other processes, have fewer craters. By counting craters, scientists can estimate the age of the surface. Here's something gentle about the Earth-Moon system. We're actually a double planet in some ways. The Moon is unusually large compared to Earth, about a quarter of Earth's diameter. Most moons are much smaller compared to their planets. The Moon likely formed from debris when a Mars-sized object collided with the early Earth, a catastrophic event that scattered material into orbit, which eventually coalesced into our Moon. the gas giants all rotate quickly, which causes them to bulge at their equators. Jupiter completes rotation in about 10 hours, spinning so fast that it's noticeably flattened. If you measure Jupiter from pole to pole versus across its equator, the equatorial diameter is about 7% larger. This bulge is a direct result of the centrifugal force from rapid rotation fighting against gravity. Let me tell you about something called differentiation. When planets were young and molten, heavy elements like iron sank to the center, forming dense cores, while lighter materials rose to form mantles and crusts. This separation by density is why planets have layered structures: core, mantle, and crust. Earth went through this process, and so did the other rocky planets. Here's a peaceful fact about cosmic time. On geological timescales, even mountains are temporary. Olympus Mons on Mars has stood for hundreds of millions of years, but even it will eventually erode away, though that process would take billions of years in Mars's thin atmosphere. Nothing is truly permanent, except perhaps the patient motion of the planets themselves. The planets experience seasons differently based on their axial tilt and orbital characteristics. Earth has moderate seasons. Mars has more extreme seasons because its orbit is more eccentric, bringing it closer to and farther from the Sun over the course of its year. Urania has the most extreme seasons, with each pole experiencing 42 years of continuous sunlight followed by 42 years of darkness. Let's consider the beauty of transits. Occasionally Mercury or Venus passes directly between Earth and the Sun, appearing as a small black dot crossing the Sun's face. These transits are rare and predictable. The last transit of Venus was in 2012, and the next won't occur until 2117. It's humbling to think about events that happen on timescales longer than human lifetimes. Here's something about Jupiter's composition. If you could scoop up Jupiter's material and compress it, you'd find it's about 75% hydrogen and 24% helium, with just 1% heavier elements. This is very similar to the Sun's composition, which makes sense because both formed from the same original nebula. In a way, Jupiter is like a star that never quite made it, lacking the mass needed to ignite fusion in its core. The atmosphere of Titan, Saturn's largest moon, is so thick and the gravity so low that if you wore wings you could actually fly there with your own muscle power. The dense atmosphere would provide enough lift, and the low gravity, about 1/7 of Earth's, would make it easy to stay aloft. It's a whimsical image, flying through Titan's orange haze. Let me share something about retrograde motion. From Earth, we sometimes see planets appear to move backward against the background stars. This is an illusion caused by the relative motions of Earth and the other planet as we both orbit the Sun. Ancient astronomers struggled to explain this strange behavior, creating complex models with circles within circles. Now we understand it's simply a matter of perspective. Here's a calming thought about the night sky. The planets we see are our neighbours, all orbiting the same star, all part of the same cosmic family. When you look at Jupiter or Saturn in the night sky, you're seeing worlds that share our history, formed from the same cloud of dust and gas that gave birth to Earth. We're connected to them through our common origin. The asteroid Vesta, one of the largest objects in the asteroid belt, has a mountain near its south pole that rises about 14 miles high, making it one of the tallest mountains in the solar system. This mountain likely formed from a massive impact that excavated a huge crater. Vesta is like a time capsule, preserving a record of the violent early solar system. Let's think about the habitable zone, the region around a star where liquid water could exist on a planet's surface. Earth sits comfortably in our Sun's habitable zone. Venus is too close and got too hot. Mars is near the outer edge and got too cold. But habitability depends on many factors beyond just distance from the star: atmosphere, geological activity, magnetic fields. It's a delicate balance. Here's something about planetary rings and their composition. Saturn's rings are mostly water ice, which is why they're so bright and reflective. Jupiter's rings are made of darker, rocky material. Uranus and Neptune's rings contain both ice and darker organic compounds. Each ring system has its own character, shaped by the moons and asteroids that created it. The surface of Mercury is covered in a fine dust called regolith, created by billions of years of micrometeorite impacts. These tiny impacts continuously pulverize the surface, creating a layer of dust several meters thick in some places. Walking on Mercury would be like walking on very fine powdery sand, though of course the extreme temperatures would make that impossible. Let me tell you about the concept of Lagrange points, special locations where the gravitational forces of two large bodies, like the Sun and Earth, balance perfectly with the centrifugal force felt by a smaller object. At these points, a spacecraft or asteroid can maintain a stable position relative to the two larger bodies. Some asteroids naturally collect at Jupiter's Lagrange points, called Trojan asteroids. Here's a peaceful fact about planetary rotation. Most planets rotate in the same direction, counterclockwise as viewed from above the solar system's north pole. This shared rotation direction is inherited from the original spinning disk of material from which the planets formed. It's like they all remember their common origin, spinning in unison. The clouds on Jupiter and Saturn are arranged in bands parallel to the equator. These bands are created by the planet's rapid rotation, which organizes the atmospheric flow into distinct zones and belts. Rising gas creates bright zones, while sinking gas creates darker belts. The pattern has persisted for as long as we've been observing these planets, a stable structure in an ever-changing atmosphere. Let's consider the temperature gradient in the solar system. The farther you go from the Sun, the colder it gets. Mercury's sunlit side can reach 800 degrees, while Neptune's clouds hover around minus 330 degrees. Yet this isn't a simple linear relationship. Venus is hotter than Mercury despite being farther from the Sun, showing that a planet's atmosphere can matter more than its distance from the Sun. Here's something about the moons of Mars. Phobos and Deimos are both very dark, reflecting only about 7% of the sunlight that hits them. They're made of dark, carbon-rich rock similar to certain types of asteroids. They're irregularly shaped, looking more like potatoes than spheres, because they're too small for their gravity to pull them into round shapes. The solar system has a center of mass called the barycenter. It's not quite at the Sun's center because the planets, especially Jupiter, pull on the Sun gravitationally. The Sun actually wobbles slightly around the barycenter as the planets orbit. For most of the time, this barycenter is inside the Sun, but sometimes Jupiter's pull moves it just outside the Sun's surface. Let me share something about impact craters on Earth. We don't see many because Earth is geologically active. Plate tectonics, erosion by wind and water, and volcanic activity all erase craters over time. The Moon, lacking these processes, preserves its craters for billions of years. By studying craters on airless bodies like the Moon and Mercury, we can learn about the impact history that Earth experienced but no longer shows. Here's a calming thought. The planets are in constant motion, yet from our perspective, they move so slowly across the sky that ancient peoples could track them without any instruments, just patient observation, night after night. This combination of constant change and apparent stability is one of the beauties of planetary motion. Neptune has supersonic winds, moving faster than the speed of sound in Neptune's atmosphere. These winds blow primarily in the opposite direction to the planet's rotation, creating a complex weather system we're still working to understand. Despite being so far from the Sun and receiving so little solar energy, Neptune has remarkably active weather. The Great Red Spot on Jupiter rotates counterclockwise, completing one rotation every 6 to 7 Earth days. Inside this enormous storm, winds reach speeds of 270 miles per hour at its edges. The storm has been shrinking over the past century, but it still dwarfs any storm system on Earth. It's a reminder of the immense scale of the gas giants. Let's think about the music we've sent to the planets. The Voyager spacecraft, which visited Jupiter, Saturn, Uranus, and Neptune, and are now heading into interstellar space, carry golden records containing sounds and images from Earth, including music from different cultures. These records are messages in bottles, cast into the cosmic ocean, carrying human creativity to the stars. Here's something gentle about seasonal changes on Mars. During winter in Mars's northern hemisphere, temperatures drop low enough that carbon dioxide from the atmosphere freezes and falls as snow, forming a layer of dry ice on the polar cap. In spring, this dry ice sublimes directly back to gas, and the cap shrinks. It's a yearly cycle of freezing and thawing, a Martian rhythm. The planets have inspired countless works of art, literature and music, from Holst's The Planet Suite to science fiction novels set on Mars, from Renaissance paintings of Venus to modern photographs from spacecraft. The planets have always captured human imagination, serving as symbols, destinations, and windows into the nature of existence itself. Let me tell you about orbital inclination. Most planets orbit the Sun in nearly the same plane, but Mercury's orbit is tilted about 7 degrees relative to Earth's orbital plane. Pluto's orbit is even more inclined, at 17 degrees. These tilts are small reminders that while the solar system is generally flat, there's still some variation, some individuality to each world's path. Here's a peaceful fact about Saturn's atmosphere. Below the visible cloud layers, conditions become increasingly extreme. Pressure and temperature rise, and eventually hydrogen gas becomes liquid hydrogen. Deeper still, the pressure is so great that hydrogen becomes metallic, conducting electricity like a metal. At Saturn's core, temperatures may reach 20,000 degrees, as hot as the surface of the Sun. The planets shine steadily in the night sky, while stars twinkle. This happens because stars are so far away that their light comes from essentially a single point, and Earth's turbulent atmosphere makes that point seem to dance and shimmer. Planets are close enough that they show as tiny disks, and the twinkling of different parts of the disk averages out, giving them a steady glow. Let's consider how planets have changed over time. Early in the solar system's history, planets migrated inward and outward from where they formed. Jupiter may have moved significantly, affecting the orbits of all the other planets. This migration helped shape the solar system into its current configuration, with the rocky planets close in and the gas giants farther out. Here's something about cometary impacts. When comets strike planets, they deliver not just impact but also water and organic molecules. Some scientists think Earth's oceans may have partly come from cometary impacts early in our planet's history. Comets are like cosmic delivery vehicles, bringing the building blocks of life across vast distances. The day-night temperature difference on Mercury is enormous, over 1000 Degrees, because Mercury has almost no atmosphere to trap heat and redistribute it. The side facing the sun bakes in intense heat, while the night side radiates heat away into space and becomes incredibly cold. It's a world of extremes without the moderating influence of an atmosphere. Let me share something about the discovery of Uranus's rings. They were found by accident in 1977 when Uranus passed in front of a star. Astronomers noticed the star's light dimmed slightly before and after Uranus blocked it, indicating rings. This discovery showed that ring systems weren't unique to Saturn, and it reminded us that the universe still holds surprises. Here's a calming thought about gravitational interactions. Every planet exerts a gravitational pull on every other planet. These influences are tiny compared to the Sun's gravity, but over millions of years they add up. The planets subtly affect each other's orbits in a complex dance of mutual influence. It's a reminder that nothing in the universe exists in isolation. The surface of Venus is hot enough to melt lead, with temperatures around 900 degrees Celsius. This heat comes from the greenhouse effect in Venus's thick carbon dioxide atmosphere, which traps heat like a blanket. Surface pressure is crushing, and the atmosphere is laden with sulfuric acid clouds. Yet despite these hellish conditions, Venus continues its slow rotation, patient and unchanging. Let's think about what makes a planet a planet. The International Astronomical Union defines a planet as a body that orbits the Sun, is massive enough for its gravity to make it round, and has cleared its orbital neighbourhood of other debris. Pluto failed the third criterion, which is why it was reclassified as a dwarf planet in 2006. It's a reminder that our classifications are human constructs, while the objects themselves simply are what they are. And as we approach the end of our journey tonight, let's remember that the planets will continue their patient orbits long after we drift off to sleep. They've been moving through space for over 4 billion years, and they'll continue for billions more. There's something deeply comforting about that constancy, that eternal motion, those ancient worlds following paths set down when the solar system was young, spinning through the darkness, illuminated by the gentle light of our sun, keeping their vigil in the vast, quiet cosmos. Rest well, my friend. The planets are still out there, still turning, still travelling their endless path through space. And they'll be there tomorrow night, and the night after, and for all the nights to come, steady and serene, our celestial companions in this corner of the universe. Sleep peacefully,